Hello, and welcome to Module 3, where we will talk about attractor logic. So attractor logic in computational design is a parametric and rule-based technique where the geometry and its properties or behavioral objects, such as how they rotate or how they scale, are influenced by their distance from specific control points or lines or curves. These are known as attractors. So let's go ahead and open Rhino. Going to escape out of this, and we're going to open Rhino, and we're going to be working with small object inches. So I'm going to go to the new, create small object inches, and I'm going to move to the perspective window, and we're going to call Grasshopper by going to the command line or by using the icon here in the upper menu. Great. So I'm going to pull up the slide again, and as you can see here, we're talking about a grid. In this case, it's grid of circles that actually have been constructed on a grid of points. And that's what we're going to be constructing. So in Grasshopper, under our vector tab, we have a subtab called grid. And under here, there's many different ways that we can actually construct our grid. So there is no explicit component that says grid of points. However, any of these would also allow us to extract points. And that's the great thing about Grasshopper. It actually explicitly shows the type of geometry that we would be constructing. So let's go ahead and select a hexagonal grid. Drag and drop that on canvas. And let's take a look at our window in Rhino. And you'll see that it actually gives us a grid of hexagons, but also it gives us a plane. If you recall from our previous tutorials, the display of the plane we can change by going to our display menu. And down here, we can change the plane size. So by default, this number is set to 8 in Rhino, which I believe is quite large. My recommendation is that for the sake of this tutorial, let's go ahead and reduce this to 1. So you always want to then enter within, and there's the preview. So here's the our grid, our hexagonal grid component. And as always, just remember that the preview of the component is determined by the way that our display options are within our display menu is set up. So my preference is to do draw icons and draw full names. And that way we're able to actually explicitly read the components, whether it's input or output, as well as recall the icon. Okay, fantastic. So let's take a look at what our grid component is showing us, the hexagonal grid. So on the input side, it tells me that there's a plane, tells me there's a size, so size of hexagonal radius. There's an extension or number of components in X direction and number of components in Y direction. And these numbers by default are set to 5. I'm going to actually lower this bar. So this is a 5 by 5, and then their size. So let's go ahead and create a slider, and we're going to change the number of our cells. Double click on canvas, create a slider 1, less than 5, less than 10, enter. And let's connect that to our X direction. So right now nothing is changing, but as I start to reduce this, you could see that our grid of hexagons are reducing in X direction. Similarly, let's copy the slider, select the slider, Control-C, Control-V, and connect it to Y direction, and you can see that that basically determines the direction in Y direction. Okay, great. So the next thing is the size factor. So right now this is set to 1. Let's make a slider that goes from going to 1, less than 1, less than 5, and enter. And if we connect this to the size factor, now that ultimately determines the scaling. And as you can see, this is scaling from 0, 0, 0, which is the original plane. And that's what we have here, right? So one thing we mentioned in the previous tutorial is that the idea of a plane or a frame is ultimately a two-dimensional vector that originates from a point, and it determines the the way that your geometry is being created. So in this case, we are creating this on the XY plane. Okay, so we're going to reset these numbers. Let's reduce this down to 1. And sometimes if you don't want to just drag the slider up and down, you can just double click, enter 1 and enter. Here, let's change this number to 1 and also this number to 1. Okay, so in this tutorial, I will also begin to further talk about data trees. Let's have a reminder. And these are slides from last time. So we have reviewed that in Grasshopper, we flow data from left to right. And then we have 3 different types of wires that we're going to come across. A single wire determines that we have only one item. A double line wire, it determines that we have a list of data, and this could be different type of data. And then when we're starting to see the dashed line, this is where we have a tree. Let's remind what that looks like. So we can have single object, we can have list of objects, we can have lists of lists, and lists of lists of lists. So please understand that we're going to be reviewing these concepts. And one of the things we're going to start to look at is this idea of applying an index. So index number is the number that we assign to our data so that we can actually find them better. And also how our data structure could determine the type of geometry that we will be constructing. Great. So let's go back to view. And let's also understand what is coming out of the output. So it is producing a cell, and sometimes depending on the geometry, you might come across that actually what it's called in this case is called a cell, but ultimately it's giving you a curve, in this case, a polyline curve. And also it's giving you a point. So it tells me that it's giving me a point, but I don't see any point preview, especially if I start to extend this. You'll see that, well, where is this point? Now, let's grab a panel and start to understand what is actually coming out of each of these. And that is always a better way for you to understand. So we can always hover over, but the panel gives us a better idea. So go ahead and double click on canvas and use a quotation mark, enter. And let's connect the output of the cells here. So it tells me that here's a polyline curve, and we're starting to see that when I have my number here, 2 by 1, I see this dashed line. So if you don't happen to have that number set up, I encourage you to change that number 2 by 1. And let's see what is coming out of the point. So double click and make another quotation mark to grab the panel, and you'll see that now it also gives me the points. So there's a couple of confusing things happening here that I'm going to go over. One is what is this point if I'm not able to see this? So certain components in Grasshopper by default, they have a predetermined preview. And sometimes they contain geometry or data, but that information is not visible. So this is one of those cases where there is information about the centroid point, but that information is not explicit. So this is one of those cases that if we go to our params tab under geometry, we can actually extract or utilize a point container, which is a container we've used before. So grab a point container. And when I do run the same information out of the output, you'll see that you're starting to see the preview of the point visualized here, right? So we're seeing that point. And whether I am looking at the output directly from the point or from the panel, the information is the same. So all this component does, it actually is generating the preview, which I believe is very helpful because you are actually starting to understand how that data correlates to geometry. Okay, so in this case, I'm going to first grab this point and I'm going to select and group it to itself. And I'm going to say that these are my cell centroids. So then this way we understand that these are the centroid points. Then let's begin to preview something else, which is focus on the data structure. Okay, so I ask everybody here to reduce the number of the slider to one by one. So we're going to change the slider a few times, and we're going to look at how our wires are changing, and that is ultimately how our data structure is changing, right? So when I do have my X number set to 1, my Y number set to 1, I'm seeing a single wire output. Single wire means there's only one component. Now, if I start to change the number only in Y direction, so pay attention in Y direction, I'm starting to get a double wire. And this is where we said that in this case, we have a list of points. So you can start to see that my list of basically the polyline cells as well as the points are expanding. So this is a polyline, a double line indicates that we have a list of information. And in this case, it could be list of polyline curves or list of points. But pay attention what happens as soon as I change the number in the X direction. This is where we're starting to get this dash line. And as soon as we get the dash line, you can see that, well, my information here started to duplicate. So in this case, what Grasshopper is doing is using this logic of data tree to begin to organize information about the columns and rows. Think about this as columns and rows in Excel, which you are able to identify a specific item. So for instance, something like this, by referring to the number as well as letter, right? So we are going to use a few different metaphor, and Excel spreadsheet is actually a great way to talk about data because it is using this two ways of monitoring in basically column based and row based. And that's one way that we can think about our data, where there is this information, which is the data tree information. And in this case, the way that our information is being organized in X direction, that is what's determining to that. So you'll see that as I increase this, that information is changing. And then there's information about number of elements in each list, right? So these are lists of lists, which is ultimately expanding in Y direction. Now, please note that this logic of X and Y is very specific to this instance of a grid making, and it's the way that the developers have packaged the information. So I want you to be careful that it doesn't, the lists and this structure is not always dependent on the grid structure. We're just using this grid as a way to talk about the way that information in Grasshopper in general is being organized. Great. So in order to do that better, I'm going to use another component similar to a panel, which is going to explain data structure a little bit better to us. So let's go to our params. Under utilities, we're going to use a component called a param viewer. And a param viewer is similar to a panel in a sense. It helps us better understand information. So before I connect to a param viewer, I ask you to reduce this number down to 1 by 1 again. And this is where I apologize, Grasshopper will get a little bit messy. We're just going to use this in the beginning to learn. And once we're more comfortable with this, we don't need to use these basically preview components. So from the cells, I ask you to drag another wire and connect it to a param viewer. And you'll see that it actually is showing me an information about how the data is being organized. So it tells me that my data has one branch, and don't pay attention to the pluralization. This is a bug in Grasshopper that whether you have one branch or multiple, it is always pluralizing it. But if we just take a look at this information, a branch is ultimately a list. So it's telling me that it has one branch and it has one element or one leaf on that branch. So it has one element. So please pay attention to my data structure here. Let's see what happens if I'm extending it in Y direction. So you'll see that it still tells me that there's one branch, in this case, one list, but the number of elements within that branch is changing, right? Great. So this is an example of how our path, this is called our data path or our data tree path, is telling us information about the information that we can find within a list. So our param viewer is completely agnostic to the type of information that we're showing here. So it doesn't care whether it's a polyline, it doesn't care whether it's a point or even text. It just tells you number of elements, right? There's also one other feature that this component has, which is a preview of information as you would see in a tree or a diagram of a tree. So please go ahead and double click on your param viewer. And I'm going to zoom in a little bit and you'll see that it tells me how my data is being organized as a tree. So you might think that, well, this doesn't really look like a tree. Think about this as a tree that only has one branch or one stem. But what is nice about this is that it is also starting to structure our information here. So I want you to pay attention to the param viewer in this case as I'm starting to change the value in X direction. So if you recall from earlier, when I changed the number in X direction, this is when we started to have the double line and we're starting to break information into multiple lists. And as you could see here, my structure, my data is starting to look more like a tree. So I'm starting to add these branches. And if I double click as well, you'll see that it's telling me that my data has 5 branches. So a branch is referring to each of these lists. And also visually, it's showing me that my data is splitting into 5 branches. So if we want to visualize that, each branch here is determined by beginning cell of your hexagon. Okay, so please keep in mind that I totally understand this information might be a little bit abstract. You might think, how might we use this information to create geometry? And we will do some of that within this tutorial and definitely more of that in the future tutorials. So in order to also better understand our path, that is the address that's associated with each of these branches and items within each branch, I want to also take advantage of another tool that we have in Grasshopper, which we'll find under Display tab, under our Vector subtab called Point List. So let's go ahead and use Point List, and we use this in our second tutorial, tutorial 2.2, in order to display the points on a curve. So this component, similar to Custom Preview, it doesn't actually provide any data output, it only provides preview. So the only caveat is that this is only taking points to visualize. So in this case, I have these centroid points that I could utilize. And let's confirm something. Because my points are generated from the cells, right? Because these are the centroid points. Therefore, my data structure of the centroid points are similar or exactly the same as my data structure for my cells. So in order to verify that, and I'm going to grab another param viewer, which we find again under parameters, under utilities, param viewer. So drag and drop this, and I'm going to connect my points either directly from here or from the geometry container. It will be exactly the same thing because ultimately this is just a visualization of the points, which then we feed to our param viewer. So if I compare this to what I have in my param viewer for the curves, you'll see that it has exactly the same data structure, right? So 5 branches for items and for items here. However, it's in my panels when I'm starting to see the difference. So it's the same data structure, but I'm starting to see then I have different elements containing here. So I have polylines here, and here I have points. Okay, so I'm going to organize this a little bit. I'm going to group these together, Control G, and I'm going to call these my data visualization for cells. And we'll do the same for these two components. I'm going to leave the point container out because we're going to use that. So go ahead and select these two, Control G, and I'm going to call this data tree visualization or centroid. Yes, it's like that. Okay, fantastic. So grouping this will allow us to have them kind of out of the way if we don't want to use them. All right, so I'm going to move them up and down, and I'm going to then select our point list, and we're going to take the centroid points, and we're going to connect them to the point input. So this component by default, it has this kind of no preview size available, so we just need to provide basically a slider. So let's grab the default slider under parameters, under input, grab the number slider and connect it to the size input. And you'll see that it's starting to emerge. And this is when we're starting to actually understand the structure a little bit better. So set it to a number that you like. And we're starting to see that we have these different structures. So this is every single one of these lists. And the number is changing from closer to 0 all the way up here. So while you have the number slider, your point preview connected, let's go ahead and change some of these sliders. So if I have my slider down to 1 by 1, that's what I'm looking at as you're starting to increase in Y direction. So we're starting to increase this way, so that is growing that way. So no matter how many I add here, I'm able to extend that. And now I'm starting to change my number of information in X direction. We're starting to replicate, right? We're creating lists of lists. And again, I want to emphasize that the way this is structured is based on how your data is being sorted inside here. We might come across another grid component that maybe number of elements in Y direction will change the data tree structure. So just be aware that this is how the specific component is set up, but it's a way for us to understand this relationship. Okay, fantastic. So before we delve into attractors, I want to talk about one other concept, which is how information inside these lists or lists of lists are organized, and what are some ways we can actually change the relationship between these points in a way that they can begin to maybe speak to one another or be part of either a larger group, or maybe we can treat them in a more specific way. So under our sets tab, there's a number of components under list, which we looked at in tutorial 2.2, including shift list. And then we have a number of components under sets under tree, which allow us to basically alter this data structure. So for instance, one of them is called flat tree, which if I hover over it, it says it's flatten a data tree by removing all branch information. So we'll come back to this for now, but just know that there are some ways that we can manipulate this data. So first, let's try to visualize this a little bit better. And I'm going to do two things. One is I'm going to turn off the grid, the background grid here. So this is a shortcut, which if you press F7, you might need to hold function F7. This is a great command to turn it on and off. It's not necessary if you do want to keep your grid off. It's just for me to visualize this better and communicate with you. I want to make this a little bit less cluttered. Great. The next thing is we're going to go and grab a component under curve, under spline, and we're going to look for a component called polyline. So a polyline ultimately needs a series of points, and it could draw a line between them. So let's go ahead and grab the polyline component. And I want us to start to understand, what does this data structure mean, and how might maybe drawing the curve sometimes show us how the data works. So I'm going to slightly move this over, and we're going to take our centroid points, and let's just connect them as is to our vertices. Here, you see that, well, it started to draw a line. So it took the first point, and then this is where I'm going to start to shift things, where we can start to look at this. So our polyline needs list of points. So in this case, this is an example of list of points. It starts from first item, and it starts to draw then to the next one, next one, next one. And then there is a break. So this acts as a break. So in this case, goes from 0, 1, 2, 3, 4, right? So that item, then there's a break, then it draws again and again and again. And that's what we're ultimately looking at. So these divisions between data trees are a way for you to break your geometry. So in this case, then it stops. Now, let's go ahead and go back to our Sets tab, and under Tree, we're going to grab this component called Flatten Tree. Flatten Tree. So grab the component and drag it here. And if you look at the icon, it basically looks like a tree that's been chopped off. So we're going to keep things almost where they are. So this time we're going to try to see, well, what happens if I flatten my tree, then draw a polyline? So I'm going to disconnect this wire that goes directly from the point to the polyline, and we can do that by either holding Control and disconnecting, or I can right-click on the input and go here to disconnect and disconnect this. So now you can see that it's orange. It means it's still waiting for information. So let's see what happens if I run my points through this component. So this component is asking for a tree, and a tree could be any type of data. When we're talking about trees again, it means it could have lists of lists. Then the output of this, I'm going to, before I connect, I'm going to double click and grab a panel. And you'll see that, well, my wire changed, right? It went from dashed line to a double line. So if I also compare this to the previous, so if I compare this panel before flattening, so as the data comes and then after flattening, you'll see that actually what flattening did, it got rid of this line. So if you look at the values, it starts from this item, the next one, next one, next one, then it continues. So it's literally like lifting out divisions, right, between this. So this is what the original method was, but then we flatten it and it made everything into one continuous list. So let's see also what happens to our data in terms of drawing a line. So if you connect this to the vertices, well, it actually did what we are expecting. So it started from 0, 1, 2, 3, 4 here, and then it continued. So it is actually treating this as one continuous list. Now, one thing I want to fix here, my points are displayed coming straight out of the centroid. So I'm going to actually move this over, and let's see how my point ordering also changes. So pay attention here before you connect this. So this is what it looks like in the beginning, right? 0, 1, 2, 3, 4, and then 0 again. But now if I just connect the output of the tree, and this is one of those cases where you see you don't need to disconnect. All you need to do is to just connect the new wire. There it is. So it actually ends with 4 and then 5 again, and then again and again and again. And it really doesn't matter how many elements you have. So let's go back to our list, and I'm going to start to extend it in Y direction. You'll see that it doesn't really care. It just extends this list and then starts again, starts again, starts again. Same thing in Y direction, right? So it is not actually, it's actually the wire type completely changed. So it doesn't really care how the data is initially constructed. It is treating it as one continuous list. So this is what flattening does, and it's a great way for you to kind of neutralize your data. Now, there's cases where we actually need to even make our data more complicated or more isolated, which is going to be the case we'll look at in later tutorial. But for now, just understand that manipulating your data is a critical approach that we need to take anytime that we want to make custom geometry. Okay, the other thing that I want you to pay attention to is how my information changed in my panel after I flattened this. So if you recall, the original one has this 3 different information, or any panel has 3 different information. It has this thing called a path, this thing called an index. An index always starts from number 0, and then it has the information of the item. So the index remained the same. All it did was it's starting to add up. The information of the geometry or the item is the same, but it actually, our path or our address got simpler, right? So it got rid of 2 different, 2 of the decimals, right? So let's also review something. Why is this component from the beginning kind of presented to us with these 3 different levels? Well, a grid is a complicated structure that, or a complex structure that is requiring us to create an array and then another array. So that's 2 levels. Plus, it has the information of the base plane. So therefore, we have 3 different index here, right? But when I'm flattening it, I'm saying I don't really actually care about that structure. Just give me everything in one place, right? So the address then doesn't need to be 3 levels deep. The other thing that I want to pay attention to is also how our param viewer changed after flattening. So let's go to our params under utilities, grab a param viewer, and let's look at our data. And in this case, I want to look at the data at the point after flattening. And you'll see that, yeah, actually it went from, and I'm going to compare it to this. It went from having 6 branches with 6 items on each branch to having 36. So 6 times 6, 36. So we didn't lose any data. We just changed the order, right? Or we just got rid of this partition. Okay, with that said, I'm going to organize my information a little bit here, so we can start to actually proceed from this point on. And before anything, I'm going to grab this flatten component and I'm going to group it with our point size. And to group this together, and I'm going to also add our param viewers and panel. So when you already have a group, if you recall, if you just select them, right click, tell it to add to group. Now everything is within one group. And I'm going to call this is our flatten centroid points. Right, so this is basically in parentheses center of cells. So you always want to use the annotation as a way that you know that you're going to go back and remember, right? So sometimes if you think centroid is going to be, it's going to take you a while to know what we're talking about, just simplify it. So center of cells. Great. The other thing is this polyline, we're actually not going to use it in geometry construction. So I'm going to turn off the preview. So select it. You can right click or use Control Q to turn off the preview. So I encourage you to keep it within this group, but we don't need to visualize it. So select it, right click and add to group. And let's go ahead and add it here. Okay, so we're going to continue from this point on, and I'm going to also do one more step, which is I'm going to take this, our original points and this group. I'm going to create a larger group, and I'm going to change the color of this group. And this is just for us to be able to identify what is kind of geometry and what is not. And I'm going to call this our center points. Okay, so let's proceed. Next thing we're going to do is we're going to draw a circle on each of these. And as a reminder, I'm going to go to this Attractor. We're trying to create something like this. So we started with this hexagonal grid, but you can imagine that this is ultimately a grid of points extracted from hexagonal centers or centroids that then have a circle draw on top, and then their size is changing based on relationship to the attractor. So meaning closer they are, larger they are, and further away they are, smaller they become. All right, let's go back to our rhino and grasshopper. And I already have the centroids, and next thing we want to do is to extract, basically draw a circle on top of these. So let's go ahead and go to our curve tab under our primitive. We've already worked with circles before, so there's a few different ways of drawing the circle. In this case, we're going to use our standard create a circle defined by base plane. This is the same thing we used in 2.2. So go ahead and drag this on your canvas, and you'll see that actually by default, it creates that preview right over your 0. And last time in 2.2, we were talking about how in Grasshopper information is being matched. I'm going to go back to the slide to talk about this. So in Grasshopper, when you are working with different types of inputs and outputs, Grasshopper takes number of elements in the smaller list or shorter list and matches it to number of elements in the larger lists, and it does whatever you tell it to do. So for instance, drawing a point is an example of that. So let's try to understand what that means. So by default, this has one plane or one origin point. Then it has one radius, it creates one circle. But what happens if, and in this case, instead of a plane, I can use the output of the tree, which are points. What happens if I provide multiple points? So if you're providing multiple points, I'm going to hover over it, in this case, 36, because my grid is 6 by 6, then it is actually providing 36 circles with the same radius. So let's take a look at our grid, and you'll see that basically this is my circle that's currently being drawn outside of my hexagon, right? Because the size of the hexagon is already default 1, and that's the radius. So therefore, the circle is starting to sit outside. So let's try something. Let's grab a default slider, go to parameters, input, and grab a number slider. And as you start to change this value, and you see that, of course, yes, it's the same radius that's being applied to all of them. So all of them are responding to this. And I'm starting to see that if this number is maybe around 0.8 or larger than that, it is going outside. So maybe somewhere around here. We can think about this maybe part of a paneling system we have to do, and we can then start to think about how to change the variation. So going back to the slide here, the way that attractor logic work here, we're saying that it's based on the distance, meaning we need to measure distance of each of these points to the attractor, and whether that's a single attractor or a multiple attractor, and based on distance, do something. In this case, for instance, change the radius of the circle. So let's go back here, and it looks like we need to look for a component called distance. And anything that has to do with distance, we're always measuring point by point. So meaning if I go to my vector tab under point, so all the components that are going to help us to work with attractors, measure distance, they're all set up under our point container here. So you can see that here, there's a component called distance. So let's go ahead and grab that. And it's asking for ultimately 2 points, point A and point B, to measure distance. And it is going to measure distance and return distance. So let's think about this. So we already have our grid of points, and that's what's coming out of our tree. But it looks like we don't have our attractor yet. So let's go ahead, go back in our Rhino. I'm going to double click on one of the default layers, and let's call it our point tractor. And let's make that an active layer. Double click, and that becomes an active layer. So let's go ahead and set up a point. So just type point in your command line, enter, and just place a point anywhere, and it could be absolutely anywhere. We're going to go ahead and change the location later on, place it anywhere within this field, right? So somewhere like this. So all we have right now is a single point, and maybe selecting red wasn't a good idea. I'm going to select a color that maybe will stand out. And later on, we can certainly change this. Great. So that's the only thing I have. So let's go ahead and go back in our grasshopper, and we're going to reference that attractor point that we just created. So let's go to our parameters under geometry, grab a point container, and let's go ahead and right click and click on set one point. And we're going to then reference this point. This is going to be our point A. And before I connect anything else, I'm going to group this to itself and say this is my point attractor. And because the point attractor, sorry for the misspelling. So because the point attractor or an attractor is something that is quite critical for us to know always where it is, I always like to change the color of whatever that needs to stand out to something that maybe looks quite different. And so in this case, I'm going to make it red, and I'm also going to change the type. So as when you group object, you can either create the box outline, or you can create it, in this case, for instance, as a blob outline. And so I'm keeping it blob, so then it really stands out and it's different. Great. So that's our attractor point that's referenced from Rhino, and we can certainly change that location later on. Then the next thing is point B. This is all the other points. So all the other points are coming out of our flattened tree component. So connect that to point B. And the color certainly changed. It meant like it has information to proceed. But let's see actually what the output is. Oops. Let's go ahead and quotation mark to grab a panel and go ahead and connect the output of distance. And you see that it actually is giving me a value. So what is the value in? What are the units? We said that in Grasshopper, the units are always determined in Rhino. And then number of distances that it's providing is exactly number of points that I have. So more points, more distances. So ultimately, what we're looking at here is from this point, which I can select and move around. I'm going to move this very close to number 0. So then this way we could actually start to see this as a gradient. So basically, I'm measuring the distance between this point, and that's the value. Then this point to that point, so that's 0, that's attractor to 1, attractor to 2, attractor to 3, etc. And based on that logic, then this should be, let's say, the furthest away, right? And in this case, it really doesn't matter where we place our point. I want you to just move it around, just make sure that the value is changing in your panel. And that becomes a way for us to then use this. Okay, fantastic. So we have our grid, we have our circles, but so far there is nothing about this that is being reflected. So before anything, I want us to first visualize what exactly the attractor could do for us. And in this case, we're actually going to take this information, so this distance information, and we're going to visualize it by extruding either our circles or our boundaries, our cells, with whatever the amount is. I want us to first see the relationship that we have here by measuring distance. So let's go ahead and go to our surface tab, and under freeform, let's grab an extrude component. So we're going to extrude. So that's under surface, freeform, extrude. And what I want to extrude is, let's say, these base circles. So we're going to grab the circles from the circle output. So just remember that all of them have the same radius, right? So right now that's a parameter that later on we will change. So grab the circles and provide it as the base geometry for extrusion. So I'm keeping the radius of the circle as is, but I want to extrude them with this distance amount. So it's asking me the vector or direction of extrusion. So let's go ahead and go to our vector tab. Under vector subtab, grab a unit z. So this is a unitized vectors, meaning the value is 1. So as soon as we connect, you'll see that your circles are extruding by unit 1. But as soon as I am going to move this over, if I, instead of a single value, right? So this is Grasshopper matching all the bases, all 36 of them, to one value. But what if I actually give it custom value? So I'm going to go ahead and do this directly from the panel. So then this way we could visualize this. Go ahead and connect this from the panel. And as soon as we do that, you'll see that actually it is starting to extrude this as kind of parametrically, right? We're starting to see this kind of create this this form. So they have different heights. So in order to visualize this better, let's go ahead and actually close these. So right now these are open extrusions. We're going to go ahead and double click and look for a component called cap. We're going to cap these openings. So use cap holes. And basically this takes any open B-wrap or a polysurface. And if you connect it now, that becomes a closed B-wrap and polysurface. And again, in order to see it better, we're going to take this one step further. Let's go to our display tab. Under preview, let's grab a custom preview. And let's go to preview and grab a custom preview. And if you connect the output of our cap holes to geometry input, I think we can visualize it a little bit better than previous kind of ghosted preview, right? So you could see that these are now extruding with different amount. So before we change anything else, let's go ahead and extend our grid a little bit more. So let's go to the beginning and change this value. Instead of 6 by 6, double click, change this to be T. And I don't want to I don't want you to drag, just enter the number. So as soon as I enter 20, I could see that, well, I initially set this up to be 10. So if you recall, to modify this, we're going to right click. We can either go to edit, and this is a way where I can extend the maximum, or you can right click and then go to values and extend the maximum from here. So for instance here, I can extend the maximum to 20 and changes. So now I can double click again and change this to 20. And you could see clearly that what would look like maybe a little bit more of a randomized relationship, we're starting to see how these heights are starting to be impacted by that one single point. Let's go ahead and also extend it in Y direction. So first we want to change the value. So let's change the maximum to 20. And kind of changes, and then double click again, change this to 20. And if you start to see that your computer maybe is lagging, and because in this case we have surfaces, you can certainly reduce this number, but I think it's quite nice when you're starting to see your geometry in quantity. And this is when we're going to go ahead and make some changes. So the only thing currently I have in Rhino is actually this attractor point. So go ahead and select it and make sure you have your gumball on. And let's go ahead and move it over. And it might take a second for it to update, but you can clearly see that now we have this beautiful landscape structure that is being impacted. And all we're doing is we're measuring distance to a single point, but you're able to create this beautiful landscape, which if you can imagine, this could be stairs, this could be planters. There's many different ways that we can use this logic, right? This could be the way that you're designing a facade system, and all we're doing is just measuring one single parameter. Okay, great. So we're going to go ahead and clean up a little bit. So first, I'm going to go to my attractor, my point attractor and distance, as well as this panel together. I'm going to group them together, Control G, and I'm going to move the color to this white color. So basically my larger groups, I'll use this white color. And I'm going to leave it as is. Then I'll just right click and say that this is our attractor distance group. Okay. And then this is our circle. I'm going to group it to itself, Control G, and this is going to be our raw circles. Then I'm going to group the rest together. So all of these 4 components, and we're going to call this extrude circles. Perfect. So in order for us to proceed, we're actually going to go ahead and turn off this extrude circles part because it actually creates a bit of distraction. Now that we understand that the logic is using distance as a way to change a parameter such as height of extrusion, that's enough for us. So I'm going to ask you to basically come to this group and select over it and use your middle mouse button to turn off the preview, or you can use Control Q to turn off the preview. So we'll do a version of this with the final changes that we make to the definition, but for now, let's go ahead and keep them to a side. Okay, so we're going to come back to the radius of the circle, and we're going to see how distance, which allowed us to extrude, is going to impact the radius. So for that, I'm going to go to the top view, and I'm going to turn off my grid. And my recommendation is where we are, let's go ahead and also reduce the cells. Double click and turn this down to 10. And also in Y direction, turn this down to 10. So we're working with a smaller, basically number of units in case your computer might be lagging. Okay, let's then go to this area. And proceed from here. Okay, so here we have, as a reminder, if we have a 10 by 10 grid, you have 100 panels or 100 plane or frames or ultimately points, and then you're giving it a single radius. But if I take all the distances and give it to the radius input, so you can just directly connect it, you'll see that it's doing something, but it's very difficult to understand this the same way that we were able to quickly understand it with the extrusion. So from top view, I'm starting to move this around. And we can clearly see that it's doing something, but it looks quite out of control. Well, the reason is that if you recall, and I'm going to connect this again, the value that in this case worked for us was quite small, right, compared to this. So a 9.8 is about 10 times larger than any number that we see here. And if I'm going even close to 1, they're starting to overlap. So of course, when I have these large numbers, these are just large circles that are overlapped together. So it looks like the logic works, but I need to somehow find a way to control these numbers. So there's two different ways we can do that. We can either take these values, because I do want to keep them proportional. I just want to make them smaller. So what if I divide them by a number? Let's try that. We're going to go to our Maths tab, and under Operators, I'm going to use a division, or you can double click and use a slash, and that becomes a division, enter. And I'm going to give it the original number as my A input, and I'm going to make a slider. I'm going to go 1 less than 10 less than 20. And if you provide that, so I'm taking that number, dividing it by a number, and then we have the output here. So immediately I'm having that 10 times smaller. So I'm going to move this over a little bit so we could build this together like this. So if I just take these numbers and connect it to the radius input, it is starting to look a little bit better, right? So this is 10 times smaller, and I can even keep going. So I can keep reducing this number, and of course, everything is proportionally scaling up and scaling down. So I can definitely use this as a starting point, and I can fine tune this number to kind of work. But what happens if I change my mind about the number of cells, and let's say I reduce this to be 20 by 20? So then I need to go back and adjust again. And then if I keep adjusting, these small ones are going to become really, really small, right? So as a designer, you're going to be facing a lot of constraints, such as relationship between material thickness and maybe minimum or maximum size of opening that you want to create. But I have to admit, it is actually creating a very beautiful pattern. So you might want to use a logic like this to create a graphic, representation of distance. But if we're talking about maybe practicality of material constraints and other maybe fabrication constraints, I don't think it's very efficient for us to keep reducing this. So there must be another way for us to remap these numbers. And that's exactly the component that we're going to be using, which is called remap. So under Maths, under Domain, we're going to use a component called remap numbers. Remap numbers. So under Maths Domain, remap numbers. And remap numbers works like a funnel. So you have a funnel of data going in, and you can scale whether the output is smaller or even larger. So let's understand how remap works. And like always, I'm going to move certain things around. And I'm actually going to select this division component and delete it. And this is one of those cases where I'm getting red here because actually this is thinking that I'm providing text. So I'm going to delete this. And that goes back to the default, which is 1. So I encourage you to not pay attention to the geometry for the next few minutes until we set this up, and then we will see the outcome. Great. So the output here, the input here, the first thing is asking me, what is the list of numbers that you want to remap? Well, in this case, it's list of distances. So I can either go directly from the output of the distance or from the panel, right? It's the same logic. It's asking me, what is the source? Meaning, what is the smallest and largest elements in the list? And then what do you want to map it to? Right? So what is the source? What do you want to map it to? So I'm going to show you a quick example in Rhino. And this is how we would be scaling geometry. And that logic actually transfers to the way that we remap data. So you can sit back and just take a look at this next minute for me to explain what scaling or remapping numbers is. So I'm actually going to just draw a random line. And here I'm going to hold shift. It goes from that point to that point, right? A random line. And I'm going to draw a random box. And here from here to that point. So a line and a box. Now I want to scale this box to be as wide as, let's say, this line, right? Or the other way around. Ultimately, there's a starting geometry or data. There's a target geometry or data. So first thing is I need to match the start point of this. So in this case, maybe I will be turning on my object snap or OSNAP. So at least this is my starting point, right? But I still need to understand what is the amount of, let's say, what's the value here and what is it that I want to map to. So if we were to just run a simple scale command, right? Select the object to scale. So that's the data that I'm providing. And in this case, it looks like a box, but it could be list of distances. Right click or enter. What is the base point? And meaning what is the start of your data? What is the scale factor or n? What is the end of the data? And what is it that I want to map it to? So we're going to use exactly the same logic to provide what it is that we want to scale, tell it what is the original size, and what do we want to map it to. So I'm going to delete this. You're not going to need it. Just I'm going to use that just as a reference. Let's call grasshopper. So therefore, when we're going back to this remap component, it's asking me what is the source, meaning what is the smallest number and largest number here. So I can certainly spend some time and look for the smallest and largest. The smallest would be always wherever or whichever one is closer to this. So for instance, 45. But as you saw earlier, if I change the number or if I have multiple point, that's a difficult task to do. It's not a good use of your time. So there's a component under maths domain called bounds. And this is going to allow us to connect. And I'm going to use another panel. We love panels. And it is going to tell me what is the smallest number and what is the largest panel number. That's ultimately what bounds is, and that's the source that I need to provide to our remap. Okay, let's organize this. And then it's asking me what is the target, meaning what is it I want to map to. So let's go ahead and provide a new target or a new domain, right? So for instance, in this case, I don't want the circle to be larger than 0.8. And I don't want it to be smaller than, let's say, 0.3, because again, fabrication constraints or maybe you want to have certain level of visibility. So let's go to our maths under domain. Let's use a component called construct domain. And by default, this is set from 0 to 1. But I'm going to grab a default slider, parameters, input, number slider, and connect the minimum to 0.25. Control C, Control V. And let's set the maximum to 0.8 and connect that as the end. I'm going to grab another panel. And ultimately, what I'm telling it is take these values and map the smallest number to that, largest number to that. And we're going to connect that as the target domain. So now if I look at my mapped output, the same numbers are mapped to always be within that, meaning if I just spend however much time I want, I'm not going to find any number that's smaller than that and larger than that. So basically, we just scale the numbers based on that. And the advantage is that I can have full control over how much and how long and everything else that determines my geometry. Okay, so we're going to group this part together, Control G. And I have to say that this remapping is a very important part, which it pretty much allows you to use attractors for many, many different operations. All you have to do is to remap. So right click on the box and let's say this is our remap distance. And Then what I want to do ultimately, all of this, we're going to bring the circle at the end. We're going to use these values to then create our new radii, right? So I can get rid of the slider. And I think the best way to view this is from top. And I'm also going to go ahead and turn off the point list, so we don't need to see that anymore. And this is again one of those cases where over time you could start to turn things off. So I'm going to select and turn this off. I'm also going to turn off the centroid points. And there's also a preview here. Select there. There you go. So we actually are starting to see a really beautiful pattern emerging where closer they are to the point, they actually have smaller openings. The further away they are, they have larger openings here. And this is where, you know, you could decide, well, maybe that's too close. And this is where we could go ahead and change this number. Maybe this becomes 0.75. And the minimum could be, again, whatever number you like. Let's take a look at this. So I think that's a really good start. And we're going to add a few different operations to this in order for us to make this field more, I think, appealing. And also along with that, explain a few other operations that you might be doing with attractors. Okay, so what we're left here is the series of circles. And we're going to go ahead and create a surface from these circles. So let's go ahead and go to our surface tab under freeform. Let's grab a boundary surface. And a boundary surface, it basically means a closed surface or a closed curve. And we're going to provide the circle as an input, and there it is. So here, I think it's easier for us to visualize this. Great. So earlier we went ahead and extruded these. So if I were to turn on the final preview, you'll see that it's still there, and ultimately it's still responding to the same point, right? So if I go to my top right now, and if I go to my, let's say, shaded view, you'll see that not only now it's changing the size of the circle, but it's also changing the height. So now we have the same parametric relationship that is corresponding to two different values, right? So I think that's quite nice. So this is a great way for us to then work with our geometry. But I think the geometry is a little bit awkward right now. We're extruding this. What I want to try to do is we want to try to actually loft between this geometry, this cell, and to the circle. So let's try to see what that might look like. So in this case, I have our surfaces, and I'm gonna add this to this group, add to group. I'm gonna go ahead and turn off the surface for now. And I'm going to also go ahead and turn off my preview here. Okay, so next thing we're going to do is we're going to also move our circles. We're going to remap the amount of moving that we're doing for our center circles. So earlier, basically, what we did, we extruded this. But what I want to do is, instead of extrusion, I want to just move them. So it's the same operation, it's the same vector that it's taking, but instead of extrusion, we're going to move. So let's go ahead, go to our transform tab under Euclidean, go to our move operation or function, and you'll see that actually it's quite similar. Difference is that this is moving geometry and this one is creating surface. So it's asking me to move. So what is it I want to move? I want to move these circles. And right now it's moving everything up with the same z value, which is 10 in z direction. But what I can do is I can just replace this with the z vector that we used earlier, and there we have it. So when I look at it like this, I can start to see that, well, that's interesting, but similar to what we said earlier, maybe you have constraints for us to maybe we can only extrude it up to a certain point, right? So this is where we can actually repeat this process exactly as is. And all we have to do is to basically use a different domain for this, different number for this. So for the sake of practice, because we are going to do this operation quite a lot, especially when we get closer to the tower, we're going to actually reconstruct this one more time. So just bear with me. I'm going to start from the distance again, and we're going to grab a remap component. So that's under maps, under domain, remap numbers. What is it that I want to remap? I want to remap all the distances. So far, so good. What is the source? So the source is this bounds, these numbers that we have already extracted. So I'm going to take the output of the bounds, but then the target number is going to be different. So let's move this remap further up here. And let's create a new domain. Let's go under maths, under domain, construct domain again. And let's make 2 sliders. And I'm going to see if I can do this above so we don't have too many wires. Let's make a slider. Let's say for my move, I want to have minimum of 1, less than 10, less than 20. Yeah. For instance, in this case, I have a height limit. I don't want to go more than 20. Enter. And for the start value, we're going to connect to 10, Control-C, Control-V. For the end value, we're going to connect to 20. That's ultimately is going to be our target domain, right? So it's exactly the same thing, it's just we're scaling it slightly differently. So here is between 0.25 to 0.75. Here is between 10 and 20. So this is an example of how you can start from one distance and create many different parametric relationships. So if I were to look at the output here, again, the panels would reflect that scaling, right? Okay, great. And before anything else, I'm going to group these together. And I'm going to say that this is my remap stance to reflect for Z. And I'm going to go back here and just say this is my remap distance to radii. Okay, great. So all we have to do is to just connect these output to the move. Sorry, let me clean this up a little bit better. So all we have to do is to just replace this number and take the output of your remap and connect it to vector Z. And you'll see that now that's a much smoother, basically, valley that you're creating. And if I change this, you can certainly make it closer to what it was, but you can absolutely change that relationship of data, right? So you can see that it's constantly changing. What you can also do is you can also reverse these numbers. And this is where an attractor could act as a repeller. So although we're going to have smaller radii if they're closer, but it's absolutely up to you how you want to remap numbers. So we don't need to stay true to the less than or closer relationship. You can take the same values and remap it the other way, right? So you can flip the minimum and maximum. and have a very different setup. So let's go with this. So this is, we're starting to do more of a repeller relationship. And you can play with these numbers, and that's what I want you to do, is to create something that you actually like. So the next thing we're going to do is I'm actually going to group this, Control G, and say this is our move circles. Great. And last thing is we're going to now actually use this top circles to then loft down to the boundary of our hexagonal cells. So in order to do that, let's go ahead and go to the original circle and turn them off. So right click, preview off, or Control Z. Now from top view, it's going to look exactly like what we had, right? But from side view, basically that circle landscape has changed. And this is how we can create maybe a really nice tile pattern that you can 3D print, or even landscape features. So now, because ultimately our circles are created from points, and that point has been extracted from our hexagonal cells, the data structure of our circles, it still matches data structure of our cells. But there's one little step that we took when we were working with our circles that we didn't take with our cell, which was this process of flattening. So if you recall, after I flattened our points, which then ultimately became the circle, centroid, and circle, our data structure changed. Now, if I want to loft between these, I need to be aware of different data structure that they follow. And this is one of those cases where if you ever feel like your grasshopper geometry is very heavy and is lagging, it's due to this discrepancy between your data. So here we use the component to flatten our information, but ultimately any data, any of these inputs or outputs, if you right click, you'll see that flattening is also an option that comes by default with the component. And we're able to flatten the data within the component. So we're going to try that. So go ahead and click on cells and then click flatten. And you'll see that as soon as you do that, actually our wires changed again. And now your data structure, it absolutely matches your data of the point after flattening. So a question that you might have at this point is, well, can I flatten my points here? Absolutely. So I don't suggest you do that because we're already flattening it here. I want to make a point that flattening and a few other operations, such as grafting, which we'll see shortly, is a way for you to isolate your geometry, bring it together as a list, or even separate them further. So for this tutorial, I recommend you flatten your cells, but still use your flatten component here in order for us to cover both ground. Okay, great. So we have these cells and we have these circles on top. Now, as we're starting to see, my definition is getting a little bit messy and I need to move back and forth. So this is one of those cases that we can use a container to actually carry information, in this case, geometry over. So let's go ahead and go to our parameters, go to our geometry tab and under curves, because ultimately these are types of curves. Connect the output of cells as the curve. And if I look at the output, it's exactly the same information, right? But what this allows me to do, and I'm going to undo this connection, it would allow me to ultimately drag this component and bring it all the way here, where I want to then do the lofting with the move circles. So I'm going to first group it to itself and say these are my cells. We have our hexagonal cells and we have our move circles. So for the extrusion, since we're not going to use it after this point on, I recommend you just move it aside. And again, over time, you'll find your own way of organizing this. So although I'm encouraging you to follow similar annotation style, but if you absolutely need more description, go ahead and adjust it as you see fit. Okay, so this is where we are right now, which is I have a series of circles that I've moved, and I have the cells, the base cells. And what I want to do is I want to loft between them. So for this, for the next operation, because I want to demonstrate a point and I don't want your computers to crash, I recommend we go back here and actually reduce this number instead of 20 by 20, double click, and let's make this 5 by 5. And you see that it's still the same logic, right? It just reduces in scale. And let's stay here. So let's now go ahead and grab a loft component. So under surface, under freeform, we're going to grab a loft component. And lofting is always looking for a series of curves. And then we can adjust the type of lofting, which we've done earlier. So you don't need to repeat this because it might crash your computer. Just pay attention to what I'm doing here. So we know from the structure here that this is a series of cells. And if I connect them as is, see what happens. It starts from item 1. It goes back here. So similar to the polyline that we do earlier, right? So actually, this is a very bad flattened surface. So if I were to just loft this, it will do that. If I were to connect both, so if I hold down Shift and connect both, you'll see that it starts from here. It basically draws this flat polyline and then it continues. So it acts exactly like our polyline, right? It becomes this continuous thing. So let's disconnect this because this is not a good idea. What we want to do instead, we want to think about the logic of this. What I want to do is I want to draw between this item and this item and this item and this item. I don't want to follow the way that it originally was, which was a way for us to only work with rows and columns, right? Similar to Excel, but I want to isolate them. So this is where we're going to go ahead and use a component called merge. So double click and look for a component called merge. This is a very useful component that we're going to use anytime that we have a data structure that's a little bit more complex. And I want us to just quickly, as a reminder of what we saw, if I provide cells, if I provide the move circles, what merge does, it ultimately just combines one set of data after another. And so polylines and circles, right? That's what we saw earlier, but that's not what I want. What I want is one polyline, one circle, one polyline, one circle. So it means actually I need to isolate them individually. And if we go to our Maths tab, sorry, under sets, under tree, there's another component right next to flatten called graphed tree. It says graph the data tree by adding an extra branch for every item. Let's go ahead and grab that. And what a grafting operation does, and I want you to just pay attention to my screen for the next few minutes, and then we'll build it together. If I provide a list to a graphed component, it actually isolates every single one of them. So I start from a list of cells here, but what grafting does, it isolates every single one of them. And if you remember from earlier, these lines are like these hard lines, which it doesn't allow your geometry or your operation to spill between these, right? So they become these divisions. So if I could graph this, and if I could graph the geometry, so graph this, these would be isolated elements that then I can just work between. So before we do anything with the merge, I'm going to disconnect. I want to disconnect here, so I'm holding Control to disconnect. Similar to flattening, grafting is an operation that we can do all the time. So if you right-click on your geometry, you'll see that there's also a graphed option, right? So grafting, arrow goes up, versus flattening, arrow goes down. So this might be a subtle, let's say cue, but trust me, over time you'll get used to it. Just pay attention to this, and if you ever, do this by mistake, you can just undo it, right click and graft. So after I also graft from here, it gives you this isolation, right? So it's isolating your elements one at a time. So then if I were to actually bypass these, at this point you understand that these are kind of previews. I'm going to just quickly go to our parameters, utilities, and grab a param viewer. I'm going to also see what happens to data. This is before grafting, right? So one branch, 25 elements, but after grafting, so 25 branch with one element, and then double click. So this is now a tree with 25 elements. I'm going to double click and move this over here. And it will be exactly the same structure here. Now, if I were to merge, and this is where I'm going to add the graph just to my cells. So then I understand that this is the same thing. Here I'm grafting within the component. I'm going to connect this. I'm going to connect this. So you'll see that actually now it's able to isolate, right? So it takes this element combines 1, 2, 1, 2. So it's matching this, and there it is. So now that these are isolated, if I then connect this to our curve input, you'll see that then they are actually lofting from here to here, from there to there, from there to there. So I think this could be a nice structure for us to work with. Let's make some slight modifications, and this is again like every few minutes go back and organize things. So one of the modifications that I want you to make, let's go ahead to here where we have draw circles, and let's turn on the preview. Now this preview is for circles before we move them. We can just replace this with top of the circle after we move them. So let's find where the moving is happening. So the moving is happening here, right? So moving is happening here. I'm going to move these closer, and then I can cap this as well. So instead of this circle having a surface preview, I'm just going to connect this. So the geometry output here, and there it is. So now these are the caps of that top. Now we can certainly also cap that. So the cap would also give us the base, but I just want you to kind of see here that we're just maybe modifying and editing as we go along. So I think that looks really nice. We're going to now use a custom preview to clean up a little bit. And before anything, I'm going to group these together. I'm going to group the merge and loft component together. Control G, and here we can say this is going to allow us to merge data and then loft. Let's do a lowercase n, and it is. And this panel, let's say I'm going to just nest it inside here, add to group, and there we have it. So let's go ahead and grab our, under display, grab our custom preview. So grab a custom preview, and I'm going to use the custom preview for the lofted surface. There it is. It's a little bit easier to see these spikes. And let's grab a color swatch on the parameters input color swatch. And click and select the color you like. Yeah, I'll go something like this, green, anything you like. And we also need to apply color to the top. So this is one of those cases where we can use the same custom preview for multiple things or have separate ones. Let's Control C, Control V or custom preview. And I'm going to connect them here. And let's slightly change the color of the cap. Maybe we add more black to it so it actually stands out more. Then let's group each of these custom preview to their components here. Select here and add to group. Great. And there we have it. So last thing, let's go back to our top view. It's a little bit easier to manipulate, and somehow along the way, my attractor point got quite far. So let's go ahead and modify this. It looks like there's a little bit of a preview issue. So some of them from top view, they don't show up, but they're all there. So from top view, let's go to the beginning and let's increase this a little bit. I recommend change this value to 10. And I recommend not dragging this, just change the number and double click in 10. And this. And again, the preview Grasshopper has an issue sometimes with preview. One thing we could try, and I'm not certain if it's going to work, but let me show you. One option is that in the upper right corner, here we can change the quality of our preview. So if I go to high quality, let's see if that changes it from top view. It looks like there's a discrepancy with what actually is showing in the geometry. Don't worry about it. We're just going to look at the perspective view because certainly we do see it in preview. So this is a warning that I have for you. Sometimes the preview in Grasshopper and Rhino might be overlapping, but that's more of a bug for the software. So as long as your geometry is there, then you should be in good hands. And there's that. And I want you to just also spend some time selecting your attractor point and just move it around. And if you start to see that your geometry is lagging, maybe reduce number of cells, but for most of you, this should be a reasonable number. Then I want you to also spend some time playing with the height. So if you recall, we have a couple of different parameters. So we've been playing with number of cells. We have our position of the attractor, which we changed. We have also our two map domain. This is how large or small and how tall our spikes are. So this is the minimum and maximum. So let's say if I make the minimum 0.5, of course, the smallest one would be smaller. If I make the maximum 0.8, this is where we're starting to enter that territory of maybe the geometry might not like it. But again, you spend some time writing an algorithm and you spend maybe double the time fine-tuning it, right? And you can reuse all of this later for other geometry. Then there's also the height. So we said that you can use these numbers if the domain start is smaller and domain end is higher, then it is acting like closer you are to the attractor, the lower this is, right? Whatever parametric relationship would set up. But you can absolutely reverse this order. So if you wanted to act like a repeller, we can then reverse this. So for instance, this could be 9, and then this is ultimately smaller, and therefore this is a powerful way of starting from a very simple thing, which is measuring distance, but look at all the complexity that we're able to drive from that. I just noticed that the slider is here floating around, so I'm going to go ahead and delete. I'm going to leave my definition up for a minute, and I'm going to walk through it with you in case you missed any flattening or anything else. So I have my hexagonal cell. So remember, we have the shortcut, Control-Alt, left-click, and that shows you where these come from. And then we're flattening the cell. So flattening was right-click and flatten. However, in the points, because I was explaining how data structure works, we're using the flattened component. We're using the point preview to understand relationships, and we drew a polyline which allowed us to understand actually how the data sometimes flows and sometimes stops between lists. We have our point attractor, which is referenced from Rhino. It's the only thing referenced from Rhino, and that ultimately allows us to measure distance of this point attractor to all the other points. And in the next tutorial, we're going to look at how you can measure distance to many different points and also a curve. Then we learned this concept of remapping information, remapping domain. And we saw the possibility of this in order to manipulate different parameters such as height of something, scale of something, etc. Earlier, we looked at an extrusion, and that is not turned off the preview for that. And instead, we did a move. And then we learned about idea of grafting, which is opposite of flattening. So grafting is when we're isolating our geometry into their single, basically containers. And similar to flattening, you can either use a component under sets, under tree for graft, or you can right-click and take any parameter and graft it. And what that allowed us to do is to isolate the geometry in a way that we can then loft from the top circle to the bottom hexagonal cell. And finally, we added custom preview to that. So I want you to spend some time modifying the colors and modifying the height and all the other parameters. And please go ahead and save your definition in your Rhino file. So your Rhino file only has a point, but I want you to also upload that. So save the document using your first name, last name, number of the first name, last name, and our basically number of our module. So follow the convention from the canvas and please upload your files. Hope you enjoyed this tutorial. Thank you very much.